Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In the last section, we have assigned all the design parameters to the STAAD Pro model. Now we'll just revisit the grouping of the members before we change the standard section, hot rolled sections to built up sections. So first of all, we shall remove the support which we had assigned to the columns in order to locate the position of the column in the plan. So go to general support, select the support and click delete. Okay, so the supports are deleted. Now go to tool, create new group. See, we have already created the groups before, so we shall revisit the grouping again. See, the columns, mesh beam, secondary beam and joist, everything has been already grouped in the previous section. So let us delete one of this group and assign them again. So go to create. We have deleted the column group. So geometry group name is select type is geometry, then columns. So columns geometry unassigned can be seen. So now take the selection cursor and select all the columns. So associate to the selected geometry, associate. So these have been associated. Now see, we had already defined and assigned various groups. So to check that, let us go to select by group name. Now see, main fixed beam, these are main fixed beam. Then click 3 main simple beam. Then secondary simple beam, then joist, then stringer, then cantilever part, then started ties, then roof brace, then vertical brace, then landing beam, then the raptor. In the simple secondary main beam, we see select only secondary main beam. Three main beams. So actually the middle beam should be also a main beam which will be transferring lateral load axially to the diaphragm. So let us group this again. The tool, create new group, select 3 main beams, associate to selected associated. So now let us go to design. and give a design command. Select the entire model. Go to command on the right side, check code, assign. So we can run it now to see if everything is working or not. For timing, I am skipping that. If you press Shift K, the nodes can be seen. So first of all, we should start from changing the sections of the joist and the simply supported, then simply supported beam, then the columns, then the main beam. Then one by one we can go on selecting and see which minimum members suffice our requirement. So let us select by group name. First of all, the joists. These are the joist. View. Now let us section the minimum section. Go to property, general, then property, then define. Properties whole section on the right hand corner side, top corner, define. Select taper die. So if we select a beam of 250 mm wave, so this beam will look something like this. This is wave 250 mm. We shall, as of now, we shall have 130 mm wide flange, 130. In thickness we shall have 4 mm, and for this we shall have 6 mm thickness. So 250 plus 6 becomes 262. Total depth 0.262. Wave thickness is 4 mm, 004 meter. Then 0.2662 again the end depth of the beam. Then flange weight is 130 mm to 1.13 meter. Then flange thickness is 0.006 mm. Add. Now let us assign this. Assign. So let us give a run. So there are 6 warnings. Let me see what are these warnings. These are movement application factors. As of now, it is of not important. Some structural engineers asked to remove it, but most of them not. So that requires a P-delta analysis, which is not in the scope of this tutorial. And usually, in most of the cases, you don't require to remove this, and many times STAAD Pro actually issues wrong warnings. So let us see what has happened to this joist. Right click, labels, design result, show diagram. Now you can see all our joists are passed. So if some joists are failed, if so red color, if red color means it is failed, so we can change the size, increase the size of the joist and rerun, and one by one we should change all the joist. Then let us go to the wall simple beam, view, whole structure, select by group. 3 main simple beam we are taking, and secondary simple beam also we are taking. View. So these are all standard section. Now let us make another section. of wave depth 300, so, and flange width 150 mm, 300.004, 4 mm is the wave thickness, 3. So 3 plus flange thickness, if we to take 8 mm, so it's become 316. Then let us take width of the flange as 150, that is 0.15 meter. Then thickness of the flange as 0.008. Add. Let us assign to all of them. Assign. Our output file was open. We have to close it before we can give a run. So give a run again. Level, show diagram. In these cases also we'll see all the beams are passed. The interaction ratios are very less. After we get interaction ratios of all the beams, we'll go frame by frame and see the possibilities of optimization when we have finished with giving built-up sections to all the required beams. View whole structures. Now let us go to the main beams, fixed main beams. Select by specification, select by group name. Joist we have covered, secondary simple beam we have covered, joist. Then let us go to the main fixed beam. Let us take same section as a simple beam. So let us give a try. 316.004.316.15.008. Assign. Let us give a run again. So right click, level, show diagram. Now see, this member is okay, this member is okay, but this member is not okay, because this has a effective length of about 4.8 meters, so it is subjected to buckling much before. This is failing because it is carrying load from the both sides. These members are failing because. So let us increase the size of this member. Select this member. The maximum ratio seems to be 1.59, so let us define its bigger section. So our last section is of 3 wave depth of 300, so let us take the wave depth at 350 and flange thickness is 10 mm, so our total depth of the beam will be 370 mm, 0.004, 0.370, 15.010. See how we are getting the size of the sections. This is our flange. This is our flange. This is our flange. And this is our flange. And this can be our web. If this is 350 mm, web depth is 350 mm. The flange thickness is 10 mm. So total depth works out to be 370 mm. So let us give a run again. Save. Let us see the results. Design results show diagram. It is still failing. We did not consider. So let us increase the size a bit. Instead of 150 mm, let us make the flange thickness as 175 mm, and let us assign these sections to this member as well. So we have this member, and this member as the main beams, as 370 mm by 200 mm flangeoid. So let us give a run again. Save. Label, design results, show diagram. So our wall flanges are okay. Now see, there is a scope of optimization. We'll cover that in next section. So this is 0.577, 0.466. So if there is a possibility of optimization or not, we'll cover that in next section. So our main beam has been okay. Now view wall structure. Now select by group name, stringer. Let us see. View or stringer size is 250 mm. Usually 250 mm is the most practical one. So this is probably failing. Let us check why this is failing at this position. View whole structure. So select by specification. Command. Let's go to command member specification. Latest plane stress. Let us show which have been provided plane stress element. Highlight. These are the This is probably failing because our plane stress slab is ending here, so we can actually move this point here. So let me create one more point here, insert node, say point 0.05. okay, sorry, select this member, right click, select insert node, 0.05, new point by distance. Okay, at one place it has been created. Insert again, insert node, 0.05, add new point. So let us merge these nodes, 1 and 1. This is 141 geometry. Merge selected node 141. Okay, then geometry, merge selected node 142. Sorry, it is geometry, merge selected node, node to keep is 142. Now let us go to the design count. This is a small portion. This should probably give wrong results. So let us go to design command, check code. See, a small piece have too much of strength, and this gap is actually shall not be there actually in actual structure. So we are toggling design command from here. Now let us see what happens to our stringer. Run analysis, save. Label, show diagram. Let us select the stringer by friction property name, ISMC, view selected object, paste shift X, so only the ratio will be seen. So see how the ratio is too much less, and at this part it is actually showing a wrong result. So this part we can actually neglect because our actual slab will be up to this point, up to the support point. So we are not taking to the support point because we do not want the deck slab to transfer lateral load in the model. As I have told, while detailing this part where we have released the effects, we should provide slotted hole so that there is a scope of movement of this stringer when a seismic load or lateral loads occur. Now let us go to view whole structure. Now we are left with the columns. Let us first select by sufficient by group name columns. Use selected object only. So let us first give this simple built-up sections. So go to property, general, property, define taper die. Let us start with 0.316, 0.004, 0.316, 0.15, 0.008. Assign. Every time you will assign, the STAAD will show post-processing results will be lost. So that has to be lost because we need to get newer sections. So let us give a run analysis again. Show diagram. See this column is okay, but none of the other column is okay. So let us define a next section. Taper die 0.370, 0.005, 0.370, 0.175, 0.010. Add, assign these sections to all the others members which are showing a failure results. So done, right click, label, design result, show. See, this column and this column is still not okay, but this is failing by bit ratio. So let us change this section a bit so that this becomes 374, this becomes 374, this becomes 0.12 flange thickness. So 350 plus 24 is equal to 374. Change. Level, design result, show. See, this is okay, but all these members are failing, so we have to go in higher sections. See, we can actually change only this part for this column and provide a joint connection here, but for this small height of 2-story building, we should actually try to provide a single column, so without a splice. So let us select all these columns which are failing. Let us define next sections. 0.3, 0.420, 0.005, 0.420, 2.012. Since we have taken 0 and 2, so we have to make the total depth of 424. Assign. Label, design result. So still our this column is still failing. So let us change these sections to 225. Change. Label, show diagram. So our all columns are okay now. Now we'll move to the raptor part. So select, you can select by specification, property name, select by group. Raptors. Then we would select also the cantilever part. View. Now this cantilever is very small, so we can take the minimum sections. So tapered eye 0.262, 0.004, 0.262, 0.13, 0.006. The smallest size. Usually made in a PV plant. Assign. Then these are our end member. So we try with same section, minimum section. And these are actually raptors which are of 12 meter span. So we should try to give a bigger sections, maybe of the same size of the column. So let us take it. Defined tapered eye 0.420, 0.005, 0.420, 0.175. Let us take 0.2, 0.010. Assign. Design result. All members are okay now. See, these members have scope of optimization. In optimization, which will actually make them a tapered section, not a uniform. As of now, they are a uniform section. If you see them, see the 3D view by selecting them, they are of uniform section. But in the next section, we will optimize them and make this raptor as tapered section as per the bending moment profile. So let us go to this. Now our 114 mm beam is okay, but our this bracing members are not okay. So So let us give a higher section database. Go to Indian pipe, 100 mm nominal bore is 114 mm outside diameter, medium, assign. Run analysis. So it is still not okay. So let us edit this. Let us take Indian section tube pipe. .165, that is 150 diameter, medium section, assign. All these force has to be assigned. Assign. Let us give a run analysis. So let us see level, design result, show diagram. This is now okay, but our two beams are now actually failing. If you see the blue color, they are critical. So we'll change these sections. Let us see what is the section 370 by 175. So let us make a section 370. General, define, taper die 374.005, 374.175.012. Assign. And what are these sections? So 316, 150. So let us make a 300. Define, taper die 0.320.005, 0.320.175.010. Assign. Now let us give it a run. Show diagram. So it seems all the members are now passed, but we should actually check it. To go to tool, go to select by section, failed beam. So you can see no beam fails on aluminum steel design calculation. So this covers the changing of sections, standard section to the built-up sections. In next sections, we'll go frame by frame and look for optimization, possibility of optimization in all these beams and columns. So our next sections will be on optimization. Thank you.